What's up, little marsupials? Today, we're going to talk about solving logarithmic equations with the same bases. I think that there are probably maybe two schools of thought as far as solving these equations go. We're going to see problems where you've got logs on both sides. So you might see like log base dose of x equals log base dose of 3x or something like that. And then you have to figure out what x is. Contrary to that, there's another school of thought, if you will, where you have logs on just one side. So you have like log base dose of 4x equals 18. And then these are solved differently, obviously, because they're different. But we're going to work on problems like these today. And I think you're going to enjoy it a lot. Yeah, all right, cool. Let's go talk about some strategy first. So if we're going to solve a logarithm, we have to do some inverse operations, right? So the first thing we want to remember is the inverse of a logarithm is an exponential. So if we have a log equation, we're probably going to have to rewrite it as an exponential to get it to work out. That's one strategy we have. Okay? So here in general are your steps for solving logarithmic equations. We want to isolate the logarithm. That means get it so that it's like log equals stuff. Okay. Once we have our log isolated, we'll rewrite it as an exponential. Then once this is written out, it should be pretty easy for us to solve for x. We might have to check for some extraneous solutions, but it's all right. We're big kids. We can plug numbers in. I'm not scared. So let's go try that. Disclaimer. You can't isolate the log here. We could move these to one side and use some condensing logs. But I think what's better here is, do you see how this is log base 2 of something equals log base 2 of something else? Well, if the logs match, the somethings have to match too. So what we can do here, because we have log base 2 of something equals another log base 2, is we can cancel the log base 2's and just say that the arguments must be equal. Cool? So if we have a log on both sides like this, we're going to just cross them out and set the arguments equal to each other. Now this is easy. We just divide both sides by 3 and x equals 5. All right, let's try it on this one. We have a natural log of some stuff equals a natural log of some stuff. So what we're going to do is cross out the natural logs, and then we're going to solve this. So we have 3x plus 2 equals 2x plus 7. I'm going to move the 2x over, trying to get all my x's together. So we're going to subtract 2x on both sides. These cancel. And then 3x minus 2x is just x. Bring down our plus 2 equals 7. And then we subtract 2. These cancel and x equals 5. Okay. Let's talk about our extraneous solutions part, because it says we need to plug these back in and check for extraneous solutions. The rule is x cannot equal a negative number. Let's rephrase that. This I don't necessarily like. This is a little bit deceiving. The inside of a logarithm cannot be a negative number. Okay? That's what it is. X can be a negative number just so long as when we plug it back in, the argument isn't negative. So let me show you on these. If I plug this back in, we get log of 3 times 5 would be 15 equals log, base 2's. I'm forgetting my base 2's of 15. This is true, and the argument is a positive number. So this is okay. This works. If we plug in 5 here, we're going to get the natural log of 5 times 3 is 15 plus 2 is 17. Positive number, we're okay. Equals the natural log of 2 times 5 is 10 plus 7 more would be 17. This is also a positive number, so that's also okay. So this works. This is fine. If we plug this in and we got something like the natural log of negative 17, we would throw this out and say, you're not allowed to plug negatives into logarithms. That's no good. Get rid of it. Okay. Let's do a couple more just for practice. This one, we can't just straight up cancel our logs because a log plus a log is not the same thing as just a single log. So what we need to do is we need to think back to our last lesson and think about how can we turn two logs into a single logarithm. Lucky for us, we know something called the product rule. And the product rule lets us take a log of A plus the log, I'm going to ahead of myself, log of B equals the log of A times B. So because we have two logs with matching bases being added together, we can condense these into a single logarithm with that same base, 10. I won't write it, it's implicit. And then we multiply their arguments. So 2 times x would be 2x equals log of 5x minus 1. Now we have log of something equals log of something. So we cancel our logs and set the arguments equal. So 2x equals 5x minus 1. Let's move the 5x over. So we'll subtract 5x on both sides to cancel. So we have negative 3x equals negative 1. We divide by negative 3 on both sides. And negative 1 over negative 3, the negative cancels the negative. So this is just 1/3 for x. If we plug this back in, 1/3 times 2 is 2/3, which is positive. And then 1/3 times 5 is 5/3 minus 3/3. This will be 2/3 also. So that one's also safe and positive. So this is our solution. Cool. So sometimes we're going to have to use those properties of exponents we learned in the last video to solve these problems. Isn't that crazy? Isn't it crazy that I teach you something and then expect you to use it one lesson later? Ugh, I can't believe the audacity of these math teachers just out here making these kids do math problems with stuff that they teach them. Are you serious? That's so inconsiderate. Let's do some more problems. Here, we have a different sort of problem. We don't have a log base 4 of something equals a log base 4 of 3. So we can't do our cancel the logs trick anymore. So this is more like what these steps we're talking about. So we're going to isolate the log. Spoiler alert, those examples are already isolated. Then we're going to rewrite the log as an exponential equation. So let's try that. All right. So when I rewrite a logarithm, the base stays the base. The exponent here is what the log is equal to. This is the exponent over here, equals the argument of the log. And then x is just 4 to the third power, whatever that is. So 4 times 4 is 16, times another 4 would be 64. So x is 64, and that's our answer. So sometimes we just rewrite it as an exponential, and then it's pretty easy. This one, our log is not isolated yet. So what we can do is we're trying to get this by itself. So let's get rid of this plus 3. Let's subtract 3 on both sides. That's good. So we have 3 times the log base 2 of x equals 9. And then this 3 is multiplying to the log. We could use our power property to put it inside on x, but then we have some exponents, and that's more complicated. I think it's easier to just divide both sides by 3 to cancel it. So we have log base 2 of x equals 9 over 3 is 3. Now we can rewrite our isolated log as an exponential equation. So our base is 2. The exponent is what the log equals. So 3 equals the argument, so x. 2 to the third power is 8. So there we go. Our answer is x equals 8. If we want to check these for extraneous solutions, we just have to make sure that when we plug this back in, the argument isn't negative. If I plug 8 in here, my argument is 8. That's a positive number, so we're good. If I plug 64 back in here, my argument is 64. That's positive, so we're good. So checked, they're not extraneous. All right, let's just do a few more examples to make sure that we can do these. Hopefully there's nothing too crazy or like out there or like intentionally malicious to make you sad, you know? And if there is, oh well, I'll guide you through there. So isolate the log first. So we're going to start by subtracting 3 on both sides. So these cancel, and we have log base 4 of 2x equals 3. Now our log is isolated, and we are going to rewrite it as an exponential. So we have 4 to the power of 3 equals 2x. 4 to the power of 3 is 64, still equals 2x. And now we have to divide both sides by 2 to get the x by itself. So our 2's cancel. 2 goes into 64 32 times. So x is 32 as our answer. We plug that back in. A positive number times a positive number. This will stay positive, so we're good and it won't be extraneous. All right. On this one, the log is isolated, except there's no base and we've got this funky thing inside. But we'll see that it's okay. So there not being a base, because this is an log log as opposed to an ln log, we know that the invisible base here is 10. So we can rewrite this in exponential form. We have 10 to the second power equals 2x minus 4. 10 squared is 100 equals 2x minus 4. And then this is easy to solve. We just add 4 to both sides. So we have 104 equals 2x. Then we divide both sides by 2. And we get that x is equal to 52. If we plug this back in, 52 times 2 is 104. Minus 4 is 100, which is positive, so it'll be okay. So check, that one will work. It's not extraneous. All right. I hope there's an extraneous one on here. Otherwise, I'm going to be sad. All right. I think these are our last 2 examples. Let's look. Oh, no. One more after that. One more? Just one more? Yeah, just one more. So 3 more examples. We're going to isolate our log. So we're going to add 3 to both sides. These cancel. We have 5 times the natural log of x plus 2 equals 10. We're going to divide both sides by 5 to cancel the coefficient of 5. So these cancel. We have the natural log of 2 plus, x. It doesn't matter. Sorry for writing it in the wrong order, but it doesn't matter. Equals 2. Now we rewrite this in exponential form because our log with the argument is isolated and we're good to go. Because this is an ln log, our invisible base is an e, as an Euler's number, the constant. So that's fine. That's fine. Don't worry. We have calculators. Let's rewrite this as an exponential. We have e to the power of 2 equals x plus 2. There, switched it back for you. Now we can subtract 2. So we have minus 2 minus 2. Actually, I don't know that I like that. Let's go ahead and plug this into our calculator. So we'll take our calculator, we'll pick it up, we'll turn it on, we'll type in e to the power of 2, we'll hit enter, and we'll get a decimal. Our decimal is 7.38906 equals x plus 2. And now we can just subtract 2. So 7 minus 2 is 5. Bring down our decimal. And that equals x. If I plug that in, a positive number plus 2 more will still be positive. So it's not going to be extraneous. And this is our solution for x. All right. If we look at this one, We want to isolate our log. We want our log to be equal to either another log or a number by itself, hopefully. So if I move this log over, in fact, put your pencil down. Put your pencil down. I'm going to do this wrong just to show you that it doesn't work. If I, maybe even let's add this log over. Put your pencil down. Don't write this. It's wrong. Log of 2x minus 3. And we're going to add that to both sides. These cancel. You have the log of x equals this log of 2x minus 3. But then you have this plus 3 over here. So the log is not isolated, right? It's got this plus 3. And if I move this over so that I have a minus 3 here, that's not going to work either. So this is bad. You don't want to do that. What we want to do here is condense these logs into one log, and then we'll have a single logarithm that we can rewrite as an exponential. So if I rewrite these using the quotient rule, then the quotient rule just says that as long as the bases match, I can rewrite it as a single logarithm with a fraction as the argument. The positive logarithm, its argument will go on the top of the fraction, and the negative logarithm, its argument will go on the bottom of the argument. Still equals 3. Now we can rewrite this in exponential form. So our base is 10. We have 10 to the third power equals x over 2x minus 3. Okay, let's simplify this. 10 to the third power, that's 1,000, equals x over 2x minus 3. Now we're going to multiply both sides by the denominator. So we're going to multiply both sides by 2x minus 3. 2x minus 3. These cancel. 1,000 times 2x is 2,000x. 1,000 times negative 3 is negative 3,000. Equals x. Let's go ahead and move this x over. Actually, let's just move these 2,000 x's over. So subtract 2,000x just to get our x's together. So these cancel. We have negative 3,000 equals negative 1,999x. Then we divide both sides by 1,999. These cancel, and we get x equals this fraction. The negatives will cancel, so they can be positive. But this is not going to reduce. This is the answer as a fraction. But I have a sneaking suspicion that your homework will want this as a decimal. So we put it in to our calculators, and we get 1.50075. And then that'll be our answer. All right, not too bad. That one's actually fun, right? We got to play with some big numbers. That's always exciting. Sometimes I feel like you guys get sheltered a little bit too much from big numbers, right? Quote unquote. Is 3,000 really a big number? I mean, 3,000 dollars? That's a lot of money. 3,000 pennies? That's a lot of pennies to have in one place, but it's not a lot of money. 3,000 grains of rice. I wonder how much rice that is. Anyway, let's do our last example and then we'll get you out of here. All right, here we see we have two logs on one side again being added, and it equals a number. So let's go ahead and just use our product rule to condense these two logs together. So we are going to have log base 6. Because they're adding, the product rule says we multiply the arguments together. So x times x is going to be x squared, and x times negative 5 is negative 5x equals 2. Now we rewrite this in exponential form. So our base is 6 the exponent of that is 2, equals x squared minus 5x. 6 squared is 36. We have x squared minus 5x over here. Because we have an x squared, what we need to do is set this equal to 0. So we're going to move the 36 over here. It doesn't have a like term because these have x's and this doesn't. So they can't combine. So here we have 0 equals x squared minus 5x minus 36. Now we have to factor this and then set its factors equal to 0 to solve for x. So we need two numbers that are going to multiply to negative 36. Our options are 1 times 36, 2 times 18, 3 times 12, 4 times 9, or I think 6 times 6. I think that's all of them. So how could we make a negative 5? I think negative 9 and plus 4. And then negative 9 times 4 would be negative 36. So this is how we're going to factor. So this is going to be 0 equals x minus 9 times x plus 4. Then we set these equal to 0. So x minus 9 equals 0. X plus 4 equals 0. Add 9 to both sides. X equals 9. Subtract 4 on both sides. X equals negative 4. And now we should probably check these. This is a complex problem. Not complex like, oh, you guys don't know about that, do you? Interesting. Not complex like the math definition. There is a fancy word in math for complex, right? But like complicated. It's a complicated problem, so we should check. So let's plug these back into the original equation and see if either of them make the argument negative. Let's start with 9. If I plug in 9, I get log of 9. That's positive, so that's fine. And then 9 minus 5, that would be positive 4, which is positive, so that's also fine. So this one is a solution. That one's fine. Let's check negative 4. If I plug in negative 4, I get log of negative 4. This is a negative argument for our log. This is bad. This is not allowed. And that means that this is an extraneous solution. We throw that away because when we plug it back in, it doesn't work. Logarithms don't take negative numbers inside. If you try and put one inside, it says, I don't want to do that. So it's extraneous. We throw it away. And our only solution is x equals 9. All right, there we go. Now you know how to solve logarithmic equations. Isn't that exciting? Do you feel accomplished? Do you feel like you've, I don't want to say if you've learned anything, because obviously you've learned something from such a excellent, exquisite, succulent video. But do you feel like you've accomplished anything? You know what I mean? Like just because you like changed the oil in your car, that's not like an maybe it is an accomplishment for some of us, but for people who like cars, it's just worrisome, right? It's just a bother. It's like, yeah, all I did was change the oil in my car today. I didn't put a new turbocharger on it or bore out the solenoid chambers for maximum floticity. You know what I mean? You didn't do any car stuff to it, but I don't know. Leave a comment below. Let me know. Make sure you like and subscribe. I'll see you guys next video. Have a great day.